Hello and welcome to Woven Chemistry. I'm Jean Weaver, and today we're going to talk about limiting reactants. This is part 4 of a 4-part series. Today we'll be working with sulfuric acid and sodium hydroxide, and I've changed the volumes a little bit to make the math here a little bit more complicated than it was in the previous reaction. As you can see, it's a beautiful afternoon here in Wisconsin, so I'm going to record this outside, and hopefully the birds won't be too noisy for the next 8 minutes. All right, let's go. Here's our reaction. Let's combine 60 milliliters of 1 molar sulfuric acid with 80 milliliters of 1 molar sodium hydroxide. This will make water and sodium sulfate, and I've included also the enthalpy change for this reaction. As you can see, it's exothermic, so if we were to actually do this macroscopically, this beaker would feel warm. Okay, so enough of that. Let's now focus in on the microscopic perspective of this reaction. And here's what I'd like you to do, is draw this reaction, and in your drawings, let's all start out with 3 sulfuric acids so that we can compare our answers more easily. And as we talked about in the last video, let's assume that the sulfuric acid completely dissociates into 2 hydrogen ions and 1 sulfate. Yes, that's not exactly accurate, but it's going to work just fine and simplify things down a bit for this explanation and this series of exercises. Okay, so pause the video and come on back when you're done. Okay, so welcome back. So like I said, we want to have 3 sulfuric acids in the first beaker. Now the question is, how much base to put into the second beaker? Well, that's a little bit trickier. Keep in mind that the balanced equation is how the chemical reacts. It's not what we have. To know how much to draw, we need to focus in on the volumes and their concentrations. And we can see that we have 60 milliliters and 80 milliliters. Well, that's a 3-to-4 ratio, so we should draw 4 sodium hydroxides in the second beaker. Okay, now let's focus on the products, and we see that we make water. Well, we can pair up 4 hydrogens with 4 hydroxides, which would lead us to 4 water molecules. Okay, let's cross those off, and we can make a couple of sodium sulfates. There's one, and here's another one. All right, and if we cross those off, we see that the second beaker, the base beaker, is all out of reactants, which makes this beaker the limiting reactant. And the first beaker has some sulfuric acid left over, which will appear in our final product beaker over here. Okay, great. Moving on to the next question. Is sketch a graph of moles versus time and show how all 4 of these substances change over the course of the reaction. Okay, so pause the video, get out your pencil and paper, and come on back when you're finished. Okay, as always, you've probably figured out that I like to set myself up a little table of start and finish quantities, or what I call a San Francisco table. And from the equation, we can see that we're going to start with 0.06 moles of the acid, 0.08 moles of the base, and obviously 0 moles of each of the products. Now let's figure out how much we use of each of the reactants. Well, to figure out how much we use, we need to take the balanced equation into account. They react in a 1-to-2 ratio. Well, we clearly do not have twice as much base as we have acid, which makes the base the limiting reactant, and that means that we will use all the base, or 0.08 moles of that. How much acid are we going to use? Well, half as much because of the 1-to-2 ratio, so we'll use 0.04. Okay, a little quick math leads us to the conclusion that we will finish with 0.02 moles of sulfuric acid left over, consistent with our particulate pictures, and no moles of the base. Okay, moving on, how much of the product are we going to make? Well, to figure that out, we have to focus on the limiting reactant in this 0.08 moles. This 0.06 moles of the acid is useless because it doesn't all get used. Okay, so again, to figure out how much we make, we also need to focus in on the coefficients in the equation. And we see that it is a 2-to-2 or 1-to-1 ratio between the sodium hydroxide and the water, which means we will make 0.08 moles of water. And now we see that it's a 2-to-1 ratio between the sodium hydroxide and the sodium sulfate, so we'll make half as much, or 0.04. Okay, and there are our totals. Okay, so if your numbers don't look exactly like mine, pause the video, correct your numbers, and then adjust your graph, and come on back when you're done. Okay, so here's how I've set my graph up. And if we start with the acid, it'll start at 0.06 and it'll go to 0.02. Again, there's some left over because it's the excess reactant. The base will start a little bit higher, but because it's used twice as fast, it will run out. Now for the products, the water will go up to 0.08 and the sodium sulfate will go half as high, again because of the 2-to-1 reaction ratio. Now let's focus in a little bit more and remind ourselves that the balanced chemical equation tells us how the chemicals react. It gives us a hint about the slopes. And if you look at the graph, we see that the blue line has twice the slope of the red line, which is consistent with the 1-to-2 ratio. And you'll see a similar thing with the green and yellow lines, a 2-to-1 ratio of their slopes. Now, the volumes and the concentrations tell us where these lines should start. They're the starting points. Okay, so let's just focus in on this a little bit more and compare it to our particulate picture. This situation's pretty complicated. Let's just focus on the products to start. And we see that we have 2 sodium sulfates and 4 waters. Well, that's perfectly consistent with 1 sodium sulfate and 2 waters, so a 2-to-1 ratio there. And if we focus in on the graph, we see that there's twice as much water made as sodium sulfate. Exactly what we see in the picture and exactly what we see in the balanced equation. Now focusing in on the reactants, well, there's only 1 reactant left in the beaker, which is consistent with what we said, that the sodium hydroxide was limiting, and our graph shows that it runs out. And there's some sulfuric acid left in the graph, which is consistent with it being left in the picture. Okay, let's now get back to that enthalpy. What would happen to the amount of heat produced if you added more sulfuric acid or more sodium hydroxide to the final product beaker? All right, well, there's a lot of stuff in this beaker, but we can ignore a whole bunch of it. All we need to focus on are the leftover reactants. Well, if we add more sulfuric acid, and there's already sulfuric acid present, nothing's going to happen. There's going to be no heat produced, no reaction. But if we add more base, that base can react with the leftover sulfuric acid, the reaction will occur, and heat will be produced. Now, challenge question. Will the temperature actually go up in this beaker? Will we feel it being warmer? Well, I really encourage you to come back and watch one of my videos about thermochemistry so you get a better understanding of the answer to that question. Okay, and that takes us to the end of this video and this series of videos. So I hope you've enjoyed it, I hope you've learned a lot, and I hope that these videos have taken your existing knowledge of chemistry, stoichiometry, limiting reactants, stretched it, deepened it, linked it, and woven it into a tight-knit and comprehensive foundation, and I really do believe that this will make your current and even future chemistry courses much easier. Okay, thank you, and please come again. Bye-bye.